Hi, welcome to this session. We will talk about an interesting problem related to AES in CTR mode. CTR stands for the counter mode. We are given this problem statement. I will walk you through this statement. The problem is, what is the message MG or MSG2, message 2 rather, for corresponding ciphertext that is given below. Okay. We are also given the plain text for message 1 and its corresponding ciphertext. So let me read this problem again. We are given message 1 and the corresponding ciphertext. The question is to figure out the message 2 based on its ciphertext 2. We are also given the IV for message 1 and we are also given the IV for message 2. So we need to figure out what is the message 2. We are also given, the question is, let's zoom in first. So we are given two plain texts. One is this A, B, 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 and then of course we are asked to find what is the second plain text. Can you find out this message? That is the part of the problem. Let's walk through the source code to understand how it's organized, what it is actually doing. We are given the main function, which is basically using AES, and then we generate the key, AES key. We walk through the plain text array. We call encrypt for each plain text using the key and an IV. An IV is generated using this get IV function. Let's take a look at what it is. So here is the get IV function, which takes the message ID as input. So in this case, I is 0, meaning message ID will be 0 to start with. So it's going to not even enter the loop because message ID is 0. So it's going to return an IV, which is just a bunch of zeros. So let's continue now. What about the second loop? The second loop will have I to be 1. It's going to call get IV function with the value of message ID is 1. So we are going to take an IV of all zeros and then increment the IV. So let's look at what increment function is doing. Increment function is basically walking through the byte array and increment by 1. That's what it is doing. So what we are seeing here is that this portion of the code is basically trying to generate a unique IV by incrementing the IV by 1, right? That's the reason we saw the IV value incremented by 1 here. Like for example, the initial IV is 0 for the message 1. For the message 2, the IV has become 1. All right. So now we understood the overall problem statement and how this text was generated for us. The question is now to reverse this ciphertext. We are given the ciphertext for message 2. We need to find out what is the message 2. How do we do that? We may have to take a quick look at the structure of AES in CTR mode. Let's do that now. So here is the NIST document I would like to share with you. Before getting into the specification, we can take a look at the graphical notation first, how the CTR mode works. So CTR mode, as the name indicates, uses so-called counters to generate the key stream. So counter in our case is first, for the first ciphertext. How did we get the first ciphertext? We got the first ciphertext block by having all the counter values to be 0. We feed it to AES, it will produce some output. Of course, we don't know the key K, but it's going to give us some output. That plain text is encrypted with that output to produce the ciphertext. We are still in message 1. Message 1 has 2 blocks now. If you remember, I had AAAs and then BBBs. So all the AAAs go here to the first block, and then all the BBBs go to the second block. Okay. How are we encrypting the second block? We take the counter value, we increment the old counter value by 1. This is how the counter mode works internally. It increments it. So the second block will be encrypted using the value 1 as the input to the block cipher, AES block cipher. So at this point, what we're getting is some kind of a key string, which we don't know because we don't know the key. The plain text of the second block will be XORed with the output that we got here. Okay. So this is how the first message was encrypted. Now let's think about how the second message was encrypted. The second message was encrypted by using the counter value. What is the counter value? Our program actually generated IV. IV becomes the counter. But as I have shown earlier, the counter for the second message starts with the value 1. It means the counter value of the first message, second block, is the same as the counter value of the first block of the second message. That's a problem. The counters are sort of stepping on each other. Counter should not be having any collision whatsoever. In this case, it has happened. So the problem is now much more easier to solve. The way we will solve is as follows. We know the plain text 2 of the first message. We also know the ciphertext 2 of the first message. We can XOR these two. If we XOR these plain text 2 with ciphertext 2, what we will get is basically this point. We will get here. We can find out what that is easily. Now, once we find out what that is, that's nothing but the key stream. That key stream is going to be the same key stream that will be used for the second message also, because the second message is going to go through the same process. The counter for the second message is going to be the same as the counter of the previous message's second block. Therefore, we don't have to worry about the lack of knowledge about the key K. It doesn't matter for us because we already know this place. That's the important thing. We already know this one. That's because we got the value here from the previous messages, XORing the plain text and ciphertext. So that's what we're going to do now. Okay, I'll show you the approach. Okay, so I will share now my problem statement and the algorithm, and then we will quickly run this. So what we are going to do, we are going to take the first message. So solution now, we will take the first message, second block, which is this one, and XOR this with the corresponding ciphertext of the first message. Okay, so I need to take the last 16 bytes of the first message. So I can find out this by looking at this. Okay, so the highlighted ones are the last 16 bytes of the first message. We are just going to do this. We are just going to XOR these two things, and then we are done. If we are done in the sense we got the key stream that we need. So we need to XOR these two. Once we are done with this, what we will do next is we will take the ciphertext of the second block, of the second message, and XOR it with the key stream. That's all. So these are the two steps. I will show you now how to do it. You can use any paper and pencil or online tool. I will just use an XOR calculator available online for us. So I will be doing XOR of these two things first. Okay, let's do that. Now I'm doing XOR to obtain the. So I'm taking this XOR, and now I'm going to use that together with the second message's ciphertext. So here comes the output. You got it. So we do know now the output of this message. Can you find out this message? Must be. You got it. Great. That's all. That's the answer. So to wrap up, what we have done is basically looked at the structure of the counter mode. We found out that the counters were overlapping. The counter number 2 of the first message happened to be the same as the counter number 1 of the second message. Therefore, we were able to find out the key stream by using the known plain text of the first message and use that key stream to decrypt the unknown plain text of the second message. That's basically what I wanted to demonstrate to you. And one more thing is that we can also take a look at the Java implementation of the counter mode. What we are seeing here is that this is the counter mode.java file, open source. So we can take a look at this. The most important thing is that it is using this increment function that we talked about. It increments the counter by value 1, not to be confused with the way I generated the IV in my Java code. So this is the internal counter that's basically incrementing each counter value by 1 for each block. And then it uses the AES or whatever block cipher algorithm that we initialized to encrypt that particular block. You see here there's an encrypt block to encrypt the counter. And then it uses that to XOR it with the input bytes that we have given. This is the place where it's doing the actual encryption. Okay, that's all I want to show you today. Thank you very much.